Okay, hello. Am I audible?
ಇಲ್ಲ ಅವರು ಏನಾಗಿದೆ ಇವರು ವಿಪ್ರಭನು ಒಂದು ಆನ್ ಮಾಡ್ಕೊಂಡಿರ್ಬೇಕು ಪ್ರಾಪರ್ಲಿ side by side both of them are there because of that reason echo. Somebody has to log out or mute. I don't know. One other the way if they are there, the echo will be there definitely. Iga matadi madam, please.
Okay, sir. Still echo is there, sir?
No, you can go on now.
Okay, sir. Thank you, sir. So, good afternoon, one and all. Myself, Dr. M. Dinamani, Associate Professor, Department of Chemistry, would like to welcome one and all to this webinar. Webinars play a very important role in keeping both students and faculties updated with the current trends in that particular area. DSCE, being an autonomous college adopting OBE, we have the liberty of assessing the outcomes of the students by various assessment tools, called as alternate assessment tools. This webinar on nanocarbon biosensors is organized by the Department of Chemistry to serve two purposes. First one being updating with the current knowledge in the particular area. And second one is evaluation of reflection notes by students for their assessment. Therefore, I request all the students to be very attentive and make use of this opportunity of listening to one of the eminent professors of National Institutes of Technology towards enriching your knowledge. Now I request our HOD, Dr. K.S. Anantraju, to formally welcome the gathering.
Very good afternoon to all. Respected today's invited speaker, Professor Ramchandra Bhatt, our beloved principal, Dr. B.G. Prasad, fellow faculty members and my dear students. Myself, Dr. K.S. Anantraju, Professor at the Department of Chemistry. It's my great privilege and honor to welcome you all on this occasion of invited talk on nanocarbon biosensors organized by the Department of Chemistry. We gather here to discuss one of the most critical topics of our time, nanocarbon towards biosensors applications. We have the privilege of hosting an esteemed speaker who will share their expertise and insights on this important subject. Today, we are honored to have Professor Ramchandra Bhatt, NITK Surathkal. Sir, on behalf of management, principal, vice principals, academic dean, Department of Chemistry, on behalf of all the students and faculty members, I welcome you, sir. Welcome you, sir. Secondly, I would like to welcome our beloved principal, Dr. B.G. Prasad, who is constantly supporting all the activities of Dayanand College of Engineering as well as the Department of Chemistry. Sir, on behalf of Chemistry Department and students, I welcome you, sir. I would like to take this opportunity to extend heartfelt welcome to the event coordinators, that is the Dr. Dinamani M and Dr. Viprabha. They coordinated this event as well as our dedicated faculty members who have played a vital role in organizing and ensuring the success of this event. Finally, I take this moment to extend a warm welcome to all our students for their special lecture, that is invited talk. I encourage all of you to actively engage in today's discussion and share your own insights. Thank you one and all. Madam, over to you now.
Thank you, sir. Now, I request our beloved principal, Dr. B.G. Prasad, to address the gathering. Sir, over to you.
Good afternoon to everyone. Respected Professor B. Ramchandra Bhatt, Professor of Chemistry at NITK Surathkal, Dr. Anantraju, HOD of the Chemistry Department and COE, Dayanand College of Engineering, all my faculty members and dear students. It's indeed a privilege to welcome all of you on this occasion of the webinar on nanocarbon biosensors by Professor Ramchandra Bhatt. He has a profound contribution in this field of biosensors, and I fully believe that with his knowledge and his experience in this field, all the students and faculty will be immensely benefited. As we all know, nanocarbon biosensors are an epitome of interdisciplinary collaboration, which involves the field of nanotechnology, engineering science, material science, all of which converge to create the revolution. And these remarkable devices, which are very minute, possess the ability to detect and measure changes in the environment, particularly biological systems, and even in the tiniest of the molecules. There's immense applications. The field of biosensors is a sort of testament to human intervention, where inventive and lot of knowledge can be gained for carrying out research as well as applications in the various fields. And this webinar, which will I think be made interactive at the end with question sessions, so that it kindles the real inquisitiveness in our students also. And I hope that the discussions and deliberations at this level, so that the impact that lies in our future generation is molded in our students, who will become the future citizens who are going to change or bring about the change in all these aspects. Because for us, it is almost, I would not say end of life, but we are all old and we are reaching our, let's say, retirement age. But for the youngsters, they will realize all these technologies, these new technologies or techniques will be applicable in more, let's say, will make a more impact in the lives, to make the human life more reasonable and responsible. At the same time, they should not get carried away, but look at the ethical, the professional ethics with which they need to work to introduce all these new technology, so that they should have a knowledge of both at both angles, whether how important, how useful it is, and but also the ethical and professional way in which they apply all these technologies. We know that technology can be used both for good as well as bad. So only the good things should be made use of for the greater good of the human being at large. And I take this opportunity to appreciate the efforts put forth by the Department of Chemistry for organizing such a webinar, and see that all our students benefit with the knowledge that is provided to them. So all the best to everyone, and for the students, enjoy the lecture, be inquisitive, and wherever required, you can ask questions and get your doubts cleared. I hope I'm not intervening in that. Dr. Bhatt will agree with that. And thank you, Dr. Bhatt, for having extended your time to present this lecture on nanocarbon biosensors. Thank you very much. Thank you very much.
Thank you, sir. Thank you very much.
Thank you, sir. So now I request our colleague, Dr. Viprabha, Assistant Professor, Department of Chemistry, to introduce today's speaker.
Very good afternoon, all. Professor B.R. Bhatt has obtained both MSc and PhD degrees from Mangalore University. After working for 6 years as lecturer in Vivekananda College, Puttur, he moved to NIT Surathkal in the year 1998. Now, he is working as a professor in Department of Chemistry, NIT Karnataka. Professor Bhatt has research on carbon nanostructure and its composites for hydrogen storage, supercapacitors, and biosensors. Mainly, he works on the gas sensors. He also works on coordination compounds and organometallic compounds as NLO materials and homogeneous and heterogeneous catalysts for organic transformations. And Professor Bhatt has published more than 130 scientific articles in reputed international journals. He has about 130 conference presentations too. The journals, scientific journals are having H-index of more than 30. And also he has published 2 books and 4 book chapters. Along with that, he was a visiting scientist at Korea Institute of Energy Research, Republic of South Korea, and he was also a Commonwealth Academic Fellow in 2015 at Northumbria University in Newcastle, UK. Professor Butt is also a visiting professor at Smart Centre, University of New South Wales, Sydney, Australia. Along with that, he has research collaborations with DLSU Manila, Philippines, BDU Brunei, Korea Research Institute of Energy, Korea Institute of Energy Research, South Korea, Northumbria University and University of East London, UK, University of New South Wales, Australia. Along with that, he has collaboration with IIT Mumbai, IIT Madras, NIT Trichy, and other Indian universities. He has obtained research grant from DRDO, DST, SERB, MHRD, and TechWay. Now, I request Professor Butt to speak over the carbon nanomaterials today. So, Professor Butt, over to you.
Thank you, Dr. Viprabha, and thank you, Dr. Prasad, sir, as well as Dr. Anantraju for the invitation. And I'm sure that whatever Prasad sir said, I agree with him. Students can ask questions probably at the end. That is would be nice. So I'll switch off my video and I'll go ahead with the audio. Today's topic is nanocarbon biosensors. Along with this technical talk, I'll be taking you virtually to NITK and Mangalore, in and around Mangalore, for the famous activities as well as food. Now, you can see that this is NH66, where the NITK campus is established on both sides, eastern and western side of the NH66. NITK is established in 1960, and we have already completed our the silver jubilee and the platinum jubilee also, and the golden jubilee. You know that today is a Saturday, and I heard that it's a working day for you after having a heavy lunch. Probably it's quite difficult for everyone to stick on to this talk, and you have no other choice. You have to attend the webinar. Probably the first reaction of you would have been this. And you know that you need to continue listening to me, and probably in sometimes you'll be engaged with such activities, and if not, probably this, if you find it bore, then we may have to see this posture. We'll try our level best to avoid this posture. And now this is again the entrance of National Institute of Technology, Karnataka, Surathkal. You can see this. This is a Agni 5 intercontinental ballistic missile. It is established or developed by DRDO. I'm very much interested in this Agni 5 ballistic missile because the carbon material, carbon composite material, which is keeping the internal temperature below 50 degrees Celsius. So carbon makes an important role here in maintaining the internal temperature of the Agni missile. And again, this is the main building of NITK Surathkal. Yeah. So coming to nano, you know that the nano, the word nano, and there's a buzz nano, what you have. This was again the nano car, what you have, and this is introduced by the Tata, Ratan Tata, thinking that this will be a common man car. But unfortunately, this could not get the market. And what exactly nano is? So we'll start with the question same as what are nanoparticles? So nanoparticle, if you define, say one definition says particles with the size in any one spatial direction within 1 to 100 nanometer. So this is the general response what you get when you ask with the nanoparticles. Now, precise response is that the particles with size in any one spatial direction within 1 to 100 nanometer, and their property being markedly different from that of the bulk. So this is very important, their property being markedly different from that of the bulk. So when the size goes to the nano level, the property changes. You can see here the different molecules are listed, and this is the scale. What you can see, it's the 0.1 nanometer, 1 nanometer, then 10 nanometer, 100, then micron, then 10 micron, 100 micron, and 1 millimeter. So you can see that these atoms, molecules comes under the within the 1 nanometer. Then you have the protein, then antibiotic, then is the DNA. DNA comes in the 1 nanometer. And then you have the virus, then you have genes, then bacteria. So the size little increases, and you can see that the hair, human hair comes around 100 microns. And the crystal. So, yeah. Coming to a different nanomaterials, the carbon nanomaterials, we'll start with the two-dimensional carbon nanostructure. Two-dimensional carbon nanostructure, the one is, the example is graphene. You can see that a elephant can be in on the one sheet of a graphene. That means to say that graphene is so hard. So then you have one-dimensional nanocarbon material, that is carbon nanotubes. Then single in that carbon nanotube, you have two different type. One is a single wall carbon nanotube, and another is a multi-wall carbon nanotube. And graphene nano ribbons also available. Then zero dimension carbon nanostructures. And that fullerenes and carbon dot comes, and then quantum dot also plays an important role as the zero D carbon nanostructures. And this is the beach approach road from NITK. We have a private beach, and I think we are the only institution is having a private beach. Now, nanotechnology is a field of research and innovation. It's concerned with the building things and devices on the scale of atoms and molecules. So in order to give a idea here, now the nano means it's a dwarf. It's actually derived from Greek. And 1 nanometer is 1 billionth of a meter, that is 10 to the power minus meter. So it's 10 times the diameter of hydrogen atom. Then you have this diameter of human hair. I said it is around 100 micrometers. So this is on average of 80,000 nanometers. And you can see here a picture where the professor, this is a nanotechnology conference where the professor is ready for giving a talk, and the MC is introducing the professor, saying that yes, the Professor Imito is a renowned nanotechnologist. As you are seeing, he is totally devoted, dedicated, and a committed scientist in this area. Now coming to the synthesis part of the synthesis part, where one-dimensional carbon nanostructures. What are one-dimensional nanostructures? So in a one-dimensional nanostructure, we have the carbon nanotubes, which can be described as a seamless cylinder made by rolling one or several layers of graphite sheet into a tubular structure. So this is a graphite sheet, you roll it, you will get carbon nanotube. And at the same time, so you can see that this is the animation where a graphite sheet is there and carbon nanotubes, multi-wall as well as a single wall carbon nanotubes. Then you have a carbon nanofiber. The carbon nanofiber, in addition to this nanotube, you have carbon nanofiber in a different form. This depending upon the arrangement of the sheets, you have fishbone type and platelet nanofibers. Now, what is the difference between the CNT as well as CNF, carbon nanotubes as well as carbon nanofibers? In carbon nanotubes, you can see a hollow core, whereas fibers, there is no hollow core. So this is the lighthouse which you can see near to our beach. And this is what I was telling is the carbon nanotube. So this is a sheet of graphene. You just roll it, you get tube. So carbon nanotubes. And this is a beach festival organized by the students. Now, nanotechnology manipulates a matter for a particular application and includes the deliberate engineering of particles by certain chemical and or physical process. There are two different types of approach for the synthesis of nanotubes or the nanomaterials. One is bottom-up production and another one is the top-down production. So you can see here the professor is asking their newly joined research students to prepare the nanomaterial, and he said that she asked the question, what are the procedure? Then he said that it's just bottom up and top down, and she was so furious. This on the lighter side. Now the synthesis of carbon nanostructures. There are there are three different major methods. So one is the arc discharge method, laser ablation method, chemical vapor deposition method. So out of these, the CVD method is the best one. Why it is best? Because you can prepare the material in a bulk scale and it's versatile and it's highly economical compared to the laser and arc discharge methods. So the advantage of the CVD method is that
Sir, we are unable to hear you.
is it all right?
Yeah, now it's
Okay. Yeah, there was some problem. Now, the disadvantages of carbon, the chemical vapor deposition method, that the CNT, CNF synthesized is having more defects compared to the other two methods, but still it is more advantageous because of the cost. And coming to the properties of the carbon nanomaterials, and you can see here, this is a Iron Man, and you know that we normally think that the Iron Man is very strong. Now, you compare the strength of the material, the carbon material with the steel, then you will come to know which is strong. So carbon nanotubes are strongest ever materials. You can see the Young's modulus, that is carbon nanotubes, is having 1250 gigapascal, and the high strength steel is having just 200 gigapascal. So around 5,000, so 5 times higher. Then carbon nanofibers is having the Young's modulus of 425 gigapascal. That's times higher in strength compared to the steel. Now, tensile strength is around 5 times or 10 times higher than the steel. Then coming to the density is much less compared to the aluminum. And that's the reason why this finds application in the spacecrafts. Then this exhibits the electrical conductivity as high as copper and exhibits the thermal conductivity as high as a diamond. And the more advantage of this carbon material is that it is highly flexible. CNTs are highly flexible. Now, until the late 1990, the output of the publications in nano field was from East Asia, Europe, and US were similar. But East Asia is now in clear lead with the US in second place. The Professor Sumio Iijima et al. In 1991 from a NEC Corporation discovered the multi-walled carbon nanotubes. You can see this picture where the professor is taking the course that is Nanotechnology 101, and professor asked the students to write the assignment, and he said, "My assignments and exams will be just like carbon nanotubes. They will be small but 100 times harder than any known material." Just by listening to that, the student has already figured his grade in his mind, that is F. Now you can see the history of the discovery of carbon nanomaterial or carbon nanotubes. So Iijima reported in 1991 that is a multi-wall carbon nanotube that's from arc discharge method, and Iijima again reported in 1993 the arc discharge method that's a single wall carbon nanotube. You can see the 10 images of single wall carbon nanotube, and in 1993 Bhuthane from IBM Corporation reported the arc discharge method for the single wall carbon nanotube. And later, the Jose Kama in 1993 reported the multi-wall carbon nanotube by CVD method, and Smale in 1995 from Rice University reported the multi-wall carbon nanotube by laser ablation method. So due to advantages of low cost, high yield, and easy setup, the research on CNT synthesis by CVD was more active when compared to these arc discharge and laser ablation methods. Now, the synthesis of CNT, that's you can see the schematic representation where A and B are the cylinders. A is argon and B is acetylene gas. We normally use precursor as acetylene because the carbon content will be high in this, and you have the two D and E furnaces. D is a preheater and E is a high temperature furnace. So you have the gas control method and the gas flow meters to control the precursor as well as carrier gas. And this is the setup what we have in our laboratory, and you can see the you can see this ceramic. So sorry, the quartz tube inside the furnace, and in the preheater place the catalyst is placed, and catalyst evaporates, give a metal nanoparticles, and that moves to the high temperature furnace where the precursor acetylene gas decomposes and deposits as carbon nanotubes. Now, how exactly the growth of carbon nanotube is predicted? So this is a mechanism for the growth of carbon nanotubes, we have two different approaches. One is a tip growth method, another one is a root growth method. Now, what happens in the furnace? The hydrocarbon vapor, which comes into the contact, they have very high temperature contact with the metal nanoparticle, and which decomposes into carbon and hydrogen species. The hydrogen flies away and the carbon gets dissolved into the metal. Then after reaching the carbon solubility limit in the metal at the temperature, as dissolved carbon precipitates out and this crystallizes in the form of a cylindrical network, which is having no dangling bonds and hence energetically stable. Now, the hydrocarbon decomposes, releases some heat to the metal exposed zone. While carbon crystallization takes place, since it is a endothermic process, it absorbs some heat from the metal's precipitation zone. This precise thermal gradient inside the furnace, that's a metal particle that keeps the process on. Now, as I said, there are two methods. One is a tip growth method or a model. Another one is a root growth model. Now, you have here substrate and the particle, nanoparticle. Substrate is on which the nanoparticle is placed. Now, in a tip growth method, what happens is the catalyst and substrate interaction, if it is very weak, then hydrocarbon decomposes onto the surface of the metal. This carbon diffuses down through the metal and CNT precipitates out across the metal bottom. This pushes the whole metal particle off the substrate. As long as the metal's top is open for fresh hydrocarbon decomposition, the concentration gradient exists in the metal, which allows the carbon diffusion, and CNT continues to grow longer and longer. So it's catalytically active ceases and the CNT growth is stopped when all this carbon, the metal is covered by the carbon. So that is tip growth. Now, what happens is when the interaction between the substrate and the nanoparticle is very strong, that gives a root growth model. So in this case, the initial hydrocarbon decomposes and the carbon diffusion takes place, similar that what I have explained for the tip growth. And then but what happens here is that the CNT precipitation fails to push the metal particle up because there is a strong interaction between the metal nanoparticle and the substrate. So the precipitation is compelled to emerge out from the metal's apex. So this at first carbon crystallizes out as a hemispherical tube, which then extends up in the form of a seamless graphitic cylinder. Subsequently, the hydrocarbon decomposes takes place on the lower peripheral surface of the metal, and as dissolved carbon diffuses upward. Thus, the CNT grows up with the crystal particle rooted on its base. Hence, this is known as a base growth method or root growth method. Now, in the picture C, you can see that the size of the nanoparticle that matters in the end product. If the size of the nanoparticle is 1 to 5 nanometer, then you get a single wall carbon nanotubes or a nanotubes. And if the size of the nanoparticle is 20 to 50 nanometer, then you get a multi-wall nanotubes. And if the size is more than 50 nanometer, then you get a nano onion. And this is the animation to show that the root growth as well as the tip growth. And you can see here this is the nanotube what we have prepared, and a catalyst particle at the tip of the grown carbon nanotube that shows it gives a proof for the tip growth mechanism. Now, the synthesis of carbon nanotubes using the different catalyst. Normally, the ferrocene is used. We have tried our different metals or different compounds for the synthesis in one step and using calcium carbonate as support. Now, the catalyst what we have used is a nickel cobalt mixture, that's a formate, then cobalt iron formate, then nickel iron formate. So this is the semi images of the carbon nanotube what we have obtained, and this is the TEM images. And you can see the Raman result, the ID by IG ratio that gives the graphitization result. And you can see that it is below 1. That shows that you get a good carbon nanotubes. And coming to the characterization of this, the XRD result shows that this is a highly graphitized material, and TGA analysis shows that the purity of thus obtained CVD method CNTs are around 99%. And the percentage yield, if you see the weight percentage, it's a very high weight percentage for nickel molybdenum formate. And we have taken the bimetallic and along with the molybdenum combination. That gives a higher result. Now, why this gives a higher result? So this can be explained in two-stage mechanism. That is, one is the number of nanotubes is determined by efficiency of nucleation stage. So this is increases with the cobalt, then platinum, nickel, and copper. So nickel is greater than copper, or cobalt is greater than copper. Then length of the nanotube is determined by the effectiveness of the catalytic growth with the defect repair stage. So here nickel is greater. So in this case, why we have chosen bimetallic? Which bimetallic? So cobalt and nickel we have taken, and that works out to be a better catalyst for the CNT preparation. And in addition to that, the molybdenum that increases the yield, and why it increases the yield, it's still a question mark for us, and we did not get the result for the reason. Now, again, the preparation using sodium chloride support. Now, the sodium chloride support, then you can see that the CNT or CNF, you can see this, the catalyst used is nickel oxalate, cobalt oxalate, or iron oxalate, and ID by IDG ratio is a little higher than 1, and that means the graphitization is a little less. And then you can see that the SEM images for this, and the SEM image shows that these are all the nickel cobalt with the ID by IG ratio of 0.91, and the iron nickel format gives 0.92 ID by IG ratio. And then you can see here the XRD for the prepared compounds, and this is actually not the CNT, this is a CNF. We have actually tried for CNT, but we ended up with the CNF. Now, we have changed, the only thing what we have done is we have changed the substrate. Now, how this works out to be a better catalyst compared to the other catalysts. See, nickel formate we have taken, and at the temperature of nearly 300 to 400 degrees Celsius. Normally, we make use of around 700 degrees Celsius in order to decompose the hydrocarbons and all. So that is the reason why the temperature is maintained a little higher. And the format, what happens is directly gives a nanoparticle, metal nanoparticles. And the byproduct, what you have, it is the hydrogen, carbon monoxide, and carbon dioxide, all are gases, and that can be escaped easily. No solid byproducts is obtained. So this is the advantage of this metal catalyst, metal format catalyst. And you can see that this is the night view of NITK. And now, why a CNF with the one sodium chloride catalyst, the substrate, and why CNT is obtained when you make use of calcium carbonate as the substrate. So this is just because there is the interaction between the metal nanoparticle and the substrate. The metal nanoparticle and the substrate, in the case of calcium carbonate as a substrate, it's very strong, and we get the CNT. And if it is the interaction is very, very, very weak, then we get the CNF. Okay, now you can see that how these fingers are decorated. So decoration definitely that gives more aesthetic look. And now we are also interested in decorating the material what we have prepared. We have prepared the CNT and CNF, and the method what we have done for the synthesis of decorated the CNT and CNF is a solvent-less method, and this is the unique method what we have reported. And is the easiest one and very simple method. So you take CNT or CNF and then metal carboxylate. Which metal you want to decorate, and take the metal carboxylate of that metal and dry mixing. So CNT or CNF metal carboxylate homogeneous mixture is formed, and if you heat this to 400 degrees Celsius under air atmosphere, then you get nano metal oxide decorated CNT or CNF. In case if you heat this 400 degrees Celsius in presence of argon atmosphere. So in the under the argon atmosphere, what happens is no oxygen will be available. Hence, the CNT and CNF will be decorated by the nano metal. Now, these are the nickel CNT, that is a nickel doped or the decorated CNTs, and nickel oxide decorated CNTs. And this is the TEM images where you can clearly see the nickel as well as nickel oxide nanoparticles are decorated on CNTs. And this is again the decoration of CNT and CNF using the palladium, and this is the TEM images for the palladium nanoparticle and palladium oxide nanoparticle CNTs. And this you can see the overview of the campus at the one end, that is the eastern side. Now, this is the palladium oxide decorated CNF, that is the carbon nanofibers. You can see the carbon nanofibers. The TEM images clearly shows you the decoration of a palladium as well as palladium oxide on CNF. Now, coming to the synthesis of the one zero-dimensional material, that is graphene quantum dots. This graphene quantum dots can be synthesized from the chemical that's as well as from the graphite and fluorines, graphenes, then carbon nanotubes. All these will be a precursor for getting the the quantum dots, graphene quantum dots. So there are different methods available in the literature. That's a top-down method, that's a hydrothermal and solothermal cutting. Then you have a electrochemical route for the synthesis. Nanolithography is another method. Nanotomy is another method. I'm not going to the detail of this. Ultrasonic shearing, then oxidative cutting. That gives again smaller pieces of the graphene sheets, nothing but the graphene quantum dots. Then scale up method, there's a bottom up method, self-assembly that gives the quantum dots, then organic synthesis approach to get the quantum dots, then sideway cage opening of the fullerene that gives the quantum dots. So this is the hydrothermal and solothermal method where the graphene oxide is taken, water and the alkali is added, and it is autoclaved for 24 hours at 200 degrees Celsius. The graphene quantum dots are obtained. You can see the black particles, that is nothing but graphene quantum dots. So this is the schematic representation for the synthesis of the graphene quantum dots. We take graphite, then KMnO4, then 9:1, the sulfuric acid and phosphoric acid. So it's using a hummus, improved hummus method. Then you get it is autoclaved, and then you get the graphene quantum dots. And this, the graphene oxide, what you get at basic pH, that can be broken into small pieces by introducing the ion beam. And this gives the graphene quantum dots. So we have used this nickel ion beam for cutting the graphene into smaller dots. You can see that this is the beach festival which is organized during the cultural festival of NITK called Incident. Okay, now what happens with the nanomaterials? The property of the nanomaterial, I said, it changes when the material property of the material changes when the size goes to the nanos level. So nanotechnology matters because a familiar material begins to develop odd property when they are of a nano size. Say, for example, tear a piece of aluminum into a tiny strips and it will still behave like aluminum. But keep chopping them a smaller and at some point 20 to 30 nanometer pieces can explode. So nano aluminum may be used as a rocket fuel also because it gives the more energy there. Now you can see this picture where it's in a company where CEO asking the labor leader to work for extra time, and then he was telling, I told you he is a union leader, even then you abused him, threatened him, and even suspended him. Then this nano behavior is quite common. So this you can see that the kite festival, which is organized during the festival in NITK. Yeah, coming to the properties of nanoparticles or nanotubes. And you can see that in case if you have an imagination or if you want to explore a ropeway to moon from Earth, only rope that can be manufactured from the nanotubes, that's carbon nanotubes or nanotubes, because it is more having a better property compared to any other. So this is an imagination, but these are not far. We may reach this level also. And the nanoparticles or nanotubes hybrids often possess interesting structural, electrochemical, electromagnetic, mechanical, and their properties that are not available to the respective components alone. As a result, they have been envisaged to be useful for catalysis, then hydrogen storage, electronic sensor devices as supercapacitors, and many other unique applications. You can see that this picture, those who have watched this Kantara movie, this is a Kambala, and this is a folk game which is very famous in the Mangalore region or Dakshina Kannada region. And coming to the application part, now for nanoparticles, the application is numerous. You take the textile side, biomedical side, health side, then the food, agriculture, then industrial, then electronics, environment, renewable energy. In all fields, you find application for nanomaterials. Then the CNTs can be can find application in as a supercapacitor, catalyst supports, then hydrogen storage material, then the automobiles, then electronics, scanning probes, biosensors, energy storage, batteries. Now, the nano batteries of the future. The size of batteries goes down and smaller day by day. So researchers have painstakingly trapped metallic lithium inside carbonaceous nanostructures. Such trapped lithium in carbon nanostructures could help make a rechargeable nano battery for next generation communication and remote sensing devices. In search of a better rechargeable battery, the researchers first produced a lithium precursor complex with dark violet color, slowly giving rise to gel-like mass. So in the presence of dichloromethane, the gel-like mass decomposed to bimetallic complex containing both lithium and cobalt. Then using this bimetallic complex, they grew thin film on the absence on any reactive gases. You can see this picture where a professor is going for a conference and a research student is sitting on the back, and then professor's wife called the professor, but he did not pick the call. Then he says, why my wife is calling and angry that I'm not responding? She called the research scholars and he says, tell her that I'm using the battery of my mobile for driving the car. These are not far because the smaller the battery, but the capacity will be high. The power density and charge density will be high, and that can be used even for as a car battery. Now, coming to the different possibility with the stimulation. Now, you have these electrons at the valency shell or the ground state. Now, when the stimuli is electronic stimulation, then what happens is you get a electrochemical output. When the stimuli is a photonic or a light, then you get a photocurrent. And in this photocurrent also, there is one more way, that is it comes back, that gives the light that is known as a fluorescence. So we have tried our level best to use this fluorescence for sensing the biomolecules. So you can see that there are different applications and the properties of these CNTs as a biosensors, because they show a promising potential for various sensing applications. And because of a very high surface area and conductivity of graphene, it makes a very interesting candidate for electrochemical sensors. And the sensing using the graphene quantum dots are customizable, which offers detection for wide range of analytes. Photovoltaics is a very promising area for even the carbon nanomaterials, that is the 2D carbon nanomaterial or 0D carbon nanomaterials. Then thin film solar cells are greatly explored for having relatively economical construction and transparent appearance. Then two different or a major hybrid thin film solar cells dye-sensitized solar cells and quantum dot solar cells. Your Dr. Viprabha has worked on dye-sensitized solar cell. And then quantum dots offer better color purity as compared to dyes and better band gap tuning opportunities. So this opens up a scope for exploring upcoming quantum dots for better quantum dot these solar cells. So this is another view of our campus. Now we have tried the sensor for sensing the glucose. Now why glucose? Know that the glucose is a source of energy, and all the cells and organs of our body needs glucose to function properly. But what happens if it is this quantity is high? So consequence of unregulated glucose level that leads to neuropathy, heart disease, blindness, skin infection, problem in the joints and especially the feet. So diabetic foot is a biggest problem, as well as a severe dehydration and leads to coma. So thinking that the severity of the glucose monitor, and we have tried our level best to approach as a sensor for glucose, and we have done a plant root nodule like the carbon nanotube composite, metal composites. So this gives the biosensor for glucose, where you have a nickel oxide and multi-wall carbon nanotube, which is using the glassy carbon electrode. You can see that the sensitivity of the material, this sensor is very high, around 6,527 ampere per mole. Then you have the LOD, limit of detection of 0.5 micromoles, and linear range is 14, and working potential is 0.5. In the graph, you can see that that's a graph A. It gives the sensitivity or the selectivity. So we, along with the glucose biomolecule, when you take the blood sample, you have different other biomolecules. So the nickel oxide multi-wall carbon nanotube, it gives a response only to the glucose and not to other any biomolecules. And this is the SEM and TEM images of the material. And you can see that we have tried with the nickel oxide multi-wall carbon nanotube. Along with this, reduced graphene oxide. They reduce graphene oxide, and this is the SEM and TEM images of these materials, and you can see that this works to be a very good sensor. And then we have tried with the graphene quantum dots. Graphene quantum dots, here you can see that the graphene quantum dots for a spectrophotometric estimation of glucose. So you can see that the graphene quantum dots is functionalized, that's the amine functionalization is done. And this amine functionalization of graphene quantum dots helps in having the binding with the glucose, and thus you get a glow here, or the estimation of glucose is possible. So the photoluminescence is obtained here because this agglomeration takes place. Agglomeration of the quantum dots takes place through the glucose. So this emission with a linear range of 0.1 to 10 millimoles and 50 to 500 millimole with an accuracy of 98 to 97%. And you can see that the amine functionalized graphene quantum dots with the variation of photoluminescence with the quantity of the glucose. So it shows that it can work as a very good sensor for the glucose. Then this is the linear graph which shows that there are the good, the R square is around 0.99971. That shows that this works out to be a very good sensor. And we have carried the interference studies for this, and it gives a response only to glucose. And the same graphene quantum dots we have tried for the copper as well as the cobalt estimation and detection. So in a copper and the cobalt estimation, why it is important? So you know that there are many reporters which gives the toxicity of copper, then mental health because of the cobalt, then the copper, cobalt, and cadmium mineral, the importance. So all these it gives then account in the present. The copper is essential for forming a red blood cells and to maintain a healthy nervous cell and immune system. This also assists in the formation of collagen found in bones and connective tissues. So adverse effect of excessive copper intake that includes vomiting, diarrhea, stomach cramp, and nausea. So in order to avoid all these, one should know the amount of the cobalt and copper present in the blood. So we have tried our level best to have a sensor for copper and cobalt. So you can see that the copper and cobalt, the UV visible absorption spectra, where the PL decreases and GQD and cobalt GQD and copper GQD, you can see the intensity decreases when it combines with the copper or cobalt. Now, why it's so? The PL quenching, here the PL quenching takes place, and this PL quenching is because the PL quenching is well utilized in fast quantitative sensing of the metal ions present in aqueous media. So this the PL quenching observed in cobalt and copper interacted GQD is due to a long-range conjugation around metal ion, which relax the exciton barrier. And what is the use of the calcium? Now, why calcium is important, and why we need to monitor calcium. The role of calcium in the blood is to circulate the blood, move muscles, and release hormones in your signal transport, formation of teeth and bone. But what happens if the amount is high? So you know that the hard water is because of the presence of calcium and magnesium salts of the salts, soluble and insoluble salts if you have. So here, that gives a say soaps come and a lime scale is formed and washing becomes difficult, hair loss, bacteria, then wrinkles happens, so stains on the utensils, then washing clothes becomes difficult. So we have tried to monitor the calcium in the hard water, and you can see that this is how the GQD is prepared. And once you prepare the GQD, then you add to the hard water, then the quenching of PL takes place. Now, in the quenching of EL is because, as I said, it's known as a turn-off mechanism, and this sensing was applied to determine the concentration of the calcium ions in aqueous media. So these are the graph which shows that this works to be a very good photoluminescence sensor. And this graph shows that the selectivity of this sensor. So it selectively responds to only calcium, not any other metals. You can see that this is the tomato, and nowadays those who grow tomato definitely becomes crorepati. So because of a very high cost. Now, why I am interested in this tomato is because of these seeds. These seeds are very rich in oxalic acid. Now, when you make sambar or rasam, you make use of tomato, and you make use of these seeds too. You just chop the tomato and use that tomato in sambar or sar, the rasam. Now, what happens is, since it is a very good source of oxalic acid, it deposits as a calcium oxalate in kidney. That remains as a kidney stone. So that results in a kidney stone. That's the reason why we thought of having one sensor to monitor this oxalic acid. So oxalic acid was monitored using the quantum dot materials. This is a graphene oxide, and this is sorry, the amine functionalized graphene quantum dot is used, and this is how the mechanism says, and I'll come to this mechanism where you have the amine functionalized graphene quantum dots and oxalic acid approaches here. Oxalic acid binds with the amine group, and then it forms the excess oxygen rich terminal groups on GQD, which can undergo reduction. And in the third picture, you can see that the bonded oxalic acid provides excess oxygen rich terminals group, which undergoes reduction, and thereby giving reduction current. And upon the reduction of the available oxygen rich terminal groups on oxalic acid, the amine functionalized graphene quantum dots, the reduction current reduces and no further site is available for the higher reduction current. And thus, the graphene quantum dots acts as a sensor for oxalic acid. So the response time for this, it is just 2 seconds, and the B selectivity can also be seen here, how it responds only to oxalic acid when you have other molecules present in the sample. And this is the present or the recent work on the sensor we are doing. That is, again, glucose using nano metal, mixed metals prepared using the hydrothermal methods and other methods. And since it's unpublished, the details will not be told too much. And you can see here the some TEM images of the material, and this works out to be very good sensor. The sensitivity and the limit of detection is 1.8 micromole, and response time is just 2.1 seconds. And this is another biosensor we are doing for cholesterol sensor. So this is a cholesterol sensor with the sensitivity of again 1370 and LOD of 0.13 micromoles. Then response time is just 2 seconds. And the recent work is on dengue sensors. So you can see here when the mosquito bites, then the dengue spreads. You can see the symptoms of dengue, that is eye pain, fever, muscle pain, headache, nausea, then bone pain, joint pain, rash, everything. Then we go to the blood test. Then you can see that the blood test gives the response to the non-structural protein dengue NS1. And how it works. So you have a glassy carbon electrode, and this is the material what we add, and this responds to the NS1, and then gives a signal through the transducer, and it amplifies, and dengue detection is possible. This is also an unpublished work, and this is the SEM and AFM results of the material. Yeah, again, coming back to the campus here, and you can see this is one of the famous food what you get in Mangalore that's called Goli Bhaji. And those who visit Mangalore definitely taste this. And coming to the end now here, you can see that the American Physical Society meeting at Caltech on December 29, 1959, Richard Feynman they considered the possibility of direct manipulation of individual atoms as a more powerful form of synthetic chemistry than those used at that time. The talk is considered to be a signal event in the history of nanotechnology as it inspired the conceptual beginnings of the field a decade later. So nanotechnology is likely to be particularly important in the developing world because it involves little labor, land, and maintenance. It is highly productive and inexpensive. It requires modest amount of material and energy. You can see the other picture where after the conference, the tea break, when he went for the tea break, he saw, he went with the plate and he did not see anything on the plate, and the chef was telling, take it, sir, whatever you like, veg, non-veg, Italian, Thai, continental, everything is in plenty. See carefully. It is nano food, sir. So this is the drone view of the institute during the Independence Day. And this is where we have housed in a science block, a chemistry department. And this is a chemistry department where I have my lab. It's a catalysis and material labs, and we take work on the materials for the coordination compounds as NLO material, nanometal oxides as a catalyst for synthetic organic chemistry. Then we have a nanomaterials for high yield synthesis, hydrogen storage, solar cells, supercapacitors, catalyst substrate, and biosensors. And then this is the credentials what we have from our lab. And definitely I need to acknowledge the funding agency, the NITK, then DRDO, MHRD, then SERB, then my collaborators from Korea, then from England, then NITK, Australia, then Australia. He is actually my student, second student working in Australia. And all this work, which is just because of hard work by all these students, 21 students are there. And I acknowledge their hard work. Because of their hard work, today I could present this beautiful work. And you can see here, this is Chuan and Greth, who got Nobel Prize in 2005 for their metathesis method of synthesis in organic synthesis. This photograph, which was taken in Rennes, France during 2008. And I hope you're all awake now. And you can see that this is ultimately we are coming to the Mangalore, where a famous ice cream parlor is there known as Ideal Ice Cream Parlor. And this is the one ice cream which has taken position in best ice creams in the world. And this is somewhere in Manila, Philippines. Thank you. And any questions? Thank you, sir. Back to you.
Sir, thank you, sir. Excellent information and presentation. No doubt that the students have gained a lot of information. We have correlated many things. I think probably most of the students, they're not in sleep mode. They're listening to all the talk because it is very interesting, and most of the materials what exactly utilized, they're multifunctional. You say from X to Z, whatever it is there. This is the material where we can say this is a wonderful substance because of the multi-functional applications. I think probably these carbon-based materials, they're all called as a superstars. Sir, from my side, one question is there, sir.
So please, sir.
Sir, as you know that last 20 years, these materials are they are called as superstars. Number one, if you take 10 years back or 20 years back, the synthesis of these nanomaterials, that is carbon-based materials, the quantum yield is very, very low. But now they are preparing in terms of tons. They have there are many companies are there from Japan and China. They are preparing these carbon-based materials. But the question is here, sir. The toxicity and the sustainability of these materials, because as you said, these materials are making wonders and they are utilizing for various applications. The concern is with respect to the toxicity and sustainability of these materials towards the environment.
Yes, sir, you are exactly right. This is the negative part of the positive research. And still the research is going on the toxicity of this material, because since it is it actually happens unnoticed many times. We may not be knowing what exactly the cause for the diseases. Since it is in the nano, many times it may go into the body also, and it may lead to different diseases. It's no doubt that many nanomaterials are used for therapy, but the side effect is still under question, sir.
Yes, sir. As you said, rightly said, sir. See, one interesting thing is that this carbon nanotube can cause us cancer, and also carbon nanotube is used to cure the cancer.
Yes, sir. Yes, that is what I said. Yeah. That is what I said. So see, it's very difficult to find out what is the cause.
Okay. Thank you, sir. Thank you very much.
Thank you, sir.
Dear madam, over to you.
Yes, sir.
The session is open now. Any question is there from the student side, they can go for it. Students, if you have any questions, the chat box is open. So anybody having any questions to the professor, you are most welcome for it.
It's Viprabha here. Sir, I have a couple of questions actually.
Please
Go ahead.
Yeah. The session was very interesting. And one more thing is, like, my question is, nowadays we are facing this. I mean, the research is going on desalination of water. Seawater. So how these carbon nano materials be useful for? Use as a membrane for that, for desalination of water. Will it be useful? I mean, nanocarbon materials.
It's no. See, definitely it will be useful, because since it is a carbon nanotubes where you have the pore size and all, but the effect is not that good still today.
Okay. Sir, one more
because
thing
polymer
is
membranes are better compared to the CNTs, and the composites are now used. The graphene is also used to composite, and then it is used as a membrane.
Okay, sir. Sir, one more is like nowadays observe that artificial sweeteners and colors, dyes are used for fruits and vegetables.
Yeah.
So is there any helpful from carbon nano sensor to detect all these artificial adulterants?
No, again, it is the selectivity. We need to do the trial and error. Then only we can say that. Yeah. Otherwise, okay. These carbon nanotubes or the carbon materials are a very good material. Definitely, it will be a sensor, good sensor. But the selectivity matters.
Yes, sir. Yeah. Thank you, sir.
Yeah.
Okay.
Sir, one of the faculty, faculty, Dr. Imoti, she's asking a question.
Yes, sir.
How do you make sure of selectivity of CQD towards metal detection through photoluminescence?
Yeah, we have done. You want me to go there?
Yes, sir. It is there in the question and answer session box. One of the
No.
The question.
You mean to say that for copper and or calcium, which one?
Madam, can you type the question here? So what exactly for?
For calcium, you have shown that the selectivity is very good compared, along with magnesium, then potassium, then sodium.
Sir, she's asking how do you make sure of selectivity of carbon quantum dots?
Yeah.
Towards metal detection through photoluminescence.
Yeah, that's what we have done one for calcium also.
Okay.
And we have done for cobalt as well as this. What we do is we take a artificial mixture and then find out the sensitivity.
Right, sir.
Is it all right?
Yes, sir. Fine, sir.
Yeah,
Fine.
fine.
Okay, sir. If there are no more questions, I think we are coming to the end of the session. Now I would like to thank formally all the people in the gathering. So first, on behalf of Department of Chemistry, Dayanand Sagar College of Engineering, I would like to express my deep sense of gratitude to today's speaker, Professor B. Ramachandra Bhatt. Sir, thank you. Your talk was informative, and our students are definitely benefited by this, and they are supposed to write a note on this, and which will be evaluated also for their alternate assessment tool. And we have these sensors are an integral part of our curriculum also. So what we discuss in the theory class is mostly basics, and the advanced applications and recent trends they have got the insights into in this webinar. Thank you very much, sir. We are thankful to you, and we will be looking forward for such webinars in future also, sir. Thank you very much. And
Thank you, madam.
Thank you, sir. Next, I would like to thank our beloved principal, Dr. B.G. Prasad, who is a constant source of inspiration for all these type of activities. Thank you, sir. Next, I would like to thank our HOD, Dr. K.S. Anantaraju, who is a constant source of inspiration as well as support in conducting all these type of activities at the department level. Thank you, sir. Next, I would like to express my sincere thanks to Captain Nagaraj, Nagaraj Subra, Professor of Strategy and Leadership, SCMS, and also Mr. Mohammed Imtiaz for sharing this Zoom link for this webinar. Thank you, sirs. Next, I would like to thank all my fellow colleagues who are directly and indirectly involved in the successful conduction of this webinar. And special thanks to Dr. Viprabha, who arranged today's speaker for this webinar. Thank you, madam. Next, I would like, and last but not the least, I would like to thank all our students for their wonderful participation in this webinar. Thank you one and all. And thank you, sir.
Professor, thank you very much, Professor, for a wonderful talk again from my side. Really,
Oh, thank you, sir. Thanks for your
really interesting. Probably our faculty members definitely they are going to trying out with respect to the materials towards sensors, because some of the faculty members seriously they are working on sensing activity.
Okay.
This will be definitely useful for them, so that any further collaboration, further interaction they wanted to have it, definitely they'll come to you, sir. Kindly help us regarding it.
Sure, sir. Sure. We are always open. And I forgot to tell you that we have a central research facilities where we have invested around 100 crore rupees. And we have almost all type of the characterization facilities. So this is available in the website also. You can make use of this procured services.
Yes.
Definitely, we'll be very happy in extending that service.
Definitely, sir. Definitely. Surely, we kindly extend your services to our characterization of the sample, especially.
Yeah.
Dr. Viprabha, anything you wanted to speak? Because sir is your guide.
No, nothing, sir.
Okay.
Thanks, Viprabha.
Yeah, thank you, sir. Thank you for
hope
the
to see you
session.
soon. Yeah, thank
Yeah.
you. Thanks, sir.
Definitely.
Thank you,
Antraj, sir.
thank you, sir. Thank you. very much.
Thank you.
Thanks for the
Thank you, sir.
opportunity.
Yes,
Yeah,
sir.
thanks,
Thank-
madam. Right.
Thank you, sir.
Okay, then I'll sign off.
Yeah. The other participants, you can leave the session now.
Imtiaz, sir, thank you very much for excellent coordination, sir.
Oh, thank you, sir.
Thank you, sir. Thank you very
Thank
much.
you, sir. Understood.